To use neural networks to learn from and process language, the first thing that you have to think about is what is the input and output representation like? So in the earlier example we saw, we had a output representation, which was a class. It was discrete, one of two classes, but the inputs were continuous real-valued numbers. Now for language, not only the outputs, but also the inputs are often things that we would naturally think of as discrete. So for example, for the way that a sentence unfolds, we want to naturally think about the context as being a sequence of discrete elements and upcoming words as being also discrete elements. So a classic kind of language processing task is the language modeling task. The incremental version of that is that we have a context, and we want to use the context to predict the next word. In order to do this, we actually have to represent the inputs in a way that can feed into a neural network, and that representation, as we saw before, has to be something that ultimately bottoms out in real-valued numbers or real-valued vectors. So let's talk about what the first most simple thing to possibly do is. The simplest thing you could do is what's called a localist, sometimes called a one-hot representation. And so to explain this, so suppose that you have a vocabulary, we'll call it vocabulary V. Okay, so the vocabulary is V. We will say that every input has is a vector of length the size of the vocabulary, and it's a one-hot vector, meaning that it has entries that are all zero except for exactly one element, and that element is going to be a value 1. Which element is it? We would arbitrarily assign an index number to each element in the vocabulary. We might use an alphabetical ordering. So if Adam is the first word in the vocabulary, then the first element of the vector will be equal to 1 when the input is Adam, and everything else will be equal to 0, and so on and so forth. Okay, so this has the advantage of simplicity. It has the disadvantage of requiring very large, long input representations. And you may remember from when we talked about word embeddings, it also has the disadvantage that there's no similarity structure that is manifest in this representation among words. And in fact, if this is the input, remember that this is going to serve in as the X's that go into the beginning of neural network processing. So all other information about the word is going to be lost once it enters the network as an input. And so there really is no mechanism with a one-hot representation for intrinsically capturing in a lexical structure a similarity structure of words. And this consideration gives rise to the idea of a lower dimensional embedding representation, which we saw before in word embedding models for vector semantics, to be used for the input representation for a language model, a neural language model as well. So here we would use a lower dimensional representation. So in this oversimplification, I would only have a length 2 representation. In general, we'll have this, let's call this dimension K. This is going to be much less than the size of the vocabulary, but it'll be large enough to actually represent differences in meanings across words. So as an oversimplification here, but something that might sort of be sort of indicative of the kinds of structures that you're going to see. So for example, here in the first dimension, you'll see that the two nouns that I have as examples have values that are pretty similar to each other, whereas the verb is very far from that. And the verb is relatively close to entities that can do the verb, and it's relatively far from entities that are less likely to so-called do the verb. So that's dealing with language inputs using embedded representations. And in fact, this idea of using a word embedding representation for a neural network approach to language was involved in one of the real milestone pieces of work on neural network models of language. This was in 2003, and it was the model of Bengio et al. And this is what's called a neural n-gram language model. So we saw the preceding example. So let's say that we want to learn a 4-gram language model that will condition on the preceding 3 words of context. So you may remember that in our n-gram modeling work that we talked about at the very beginning of the semester, the traditional approach is a multinomial distribution. of p w sub I given w sub I minus 3, w sub I minus 2, w sub I minus 1. And that would mean that for every distinctive context, we would keep a separate multinomial distribution around, and we would have to learn different multinomial distributions. We might use back-off methods where we use a mixture of a trigram and a fourgram and a bigram model and do things. But basically, the fundamental ingredients would be the counts of multi-word sequences, the raw counts, and we would mix those counts together in some way. The neural n-gram language model said, no, we're not going to do that. We're going to include the previous 3 words of context, say in a fourgram model, but we're going to do something fundamentally different than we did before. So let's remember from the word embedding approach, let's say that we have a k-dimensional word embedding representation, then we would have this some matrix C, and C is going to be of dimension, it will be k columns, and it will be the size of the vocabulary rows, and for the ith word, the ith row will pick out an embedding representation. And this part of the model says that the input to the network is that a word's meaning representation, or its input representation, is going to be invariant to which word of the context it is. Rather, it's going to have an embedding representation that is simply looked up from a table and entered in as one part of the input to the neural network. The inputs of the 3 preceding words are concatenated with each other, and then that concatenated input all points to the hidden layer. And that means that the hidden layer we might represent, for example, as if we call this representation X, this concatenated representation X, then we would say that the hidden layer activation, H, is equal to some nonlinear function. In this case, it's the tan H function of a weight matrix, WH, times the input X. And we might also add a bias function. In this case, I'm explicitly representing the bias function in the model formula specification. Last time we looked at the bias function as implicit as one of the nodes. At any rate, this hidden layer then is passed on through another transformation here, another linear transformation, and then you have the softmax that gives the probability distribution of the word in its context. That is, you are doing what you can think of as neural generalization over the neural generalization over the words in the context, putting them together in a hidden layer, because the weights for the word -3, word -2, and word -1, those weights that connect these things could be different. There is a positional memory that is implicit in the differing weights. Even though the word that's being looked up is the same in the 3 cases, it's going to contribute in a different way to the hidden layer. And then the hidden layer itself is what predicts the next word. So that's the neural n-gram model. And this was a very influential model. Just to show you the performance, you're familiar with perplexities. And this is already quite old work at this time. But even then, so the bottom here, we have n-gram language models that you're familiar with. And for the data sets that they were looking at, they had validation and test set perplexities around 300. And you can see that the neural language models had massive improvements over that, getting things down to between 250 and maybe 300. And so that was really a huge improvement. So there's dramatic improvement in results relative to these multinomial n-gram models. And so that was a very early result relative to the contemporary era of deep learning, but it showed even in the n-gram context that there was really a lot of potential power associated with this kind of modeling technique. And so that's the neural n-gram model. So we have inputs, hidden layer, output. And now we knew that going in that we would want to have something that looked like this overall for a neural network model for language, but this gives one instance of what it would look like. So what is the input? The input is the concatenation of a embedding representation of each of the 3 preceding words in the in the context. The hidden layer is some is learned. And then the output is of size of the vocabulary, and you do a softmax operation to put a probability distribution over next words. This has advantages over traditional n-gram modeling. The most crucial advantage is that it generalizes over n-gram contexts. So this model has the capacity, because it has an embedding representation, it has the capacity to learn that, for example, if soup appears in the context, it should probably generate reasonably similar predictions as if another word, for example, like broth, that is semantically similar to it, broth should generate similar predictions. Okay, and this model was able to do that, and that leverages the sort of similarity structure among contexts in a very flexible way that can be learned on its own. It doesn't have to be hand-coded, and that's extremely powerful. But there are also some limitations of the neural n-gram model. First of all, this is for a fixed dimensionality input context. So we have to pre-specify that there are only 3 words that are being attended to in the preceding context. The question then arises, well, how do we model variable length contexts? So sentences can be of arbitrary length, and we can't specify what the dimensionality of the input is of the preceding context all on its own. And so in the next part, we're going to look at models that extend beyond this fixed dimensionality input and use a mechanism called recurrence to very flexibly attend to context that is arbitrarily potentially distant from the next upcoming word. And we'll continue with that in a moment.